Alright, so in this video, we'll be looking at a rather challenging and long empirical formula problem. It'll be covering empirical formula, molecular formula, hydrated organic compounds, combustion analysis, really a bunch of things put into one problem. And so if you're able to figure this one out, I'm sure you can figure out really any other problems, empirical formula problems, your teachers may throw your way. But getting right into it, we see that we have a 5-gram sample of an unknown hydrated organic compound composed of carbon, hydrogen, and oxygen, and the water of hydration, and this was all combusted completely. This reaction produced 7.333 grams of carbon dioxide and 2.999 grams of water, and after heating a separate 5-gram sample of this compound, 0.900 grams of water was lost due to dehydration. And we're given that the molar mass of the anhydrous compound, that is the compound excluding that water of hydration, was 148 grams per mole. And we need to find the empirical formula, the molecular formula, and the value of X in the hydrate form. And again, remember, this empirical formula and molecular formula are for the anhydrous compounds. But starting off, whenever we're given this sort of combustion analysis type of problem, it's best that you always start with the combustion products, that is carbon dioxide and water. And that's because it's from these that we can figure out how much carbon and hydrogen were present in the original compound. So in this case, we start with our 7.33 grams of carbon dioxide, which we're trying to convert into moles and then convert that to moles of carbon. So we just divide by our molar mass, which, trust me when I tell you, is 44.01 grams of carbon dioxide per mole of carbon dioxide. And this is a calculation I did off screen, but if you wanted to do it yourself, again, that would be pretty straightforward. You would just add up your molar masses of the individual elements that make up the compound, and that information, again, is available on your periodic table. So arranging this, we can cancel out our grams, giving us an answer of 0.1667 moles of CO2. And remember, we wanted our moles of carbon, but looking at our chemical formula of carbon dioxide, we see that for every 1 mole of carbon dioxide, we actually have 1 mole of carbon. And that means that this answer is also equal to our moles of carbon. Now, we do the same thing for our water. Again, starting with 2.999 grams of H2O. And again, trust me, the molar mass is 18.02 per mole of H2O. Canceling out our grams gives us an answer, 0.1665 moles of H2O. But unlike the last step, this actually is not equal to our moles of hydrogen. And why is that? Well, again, just look at our chemical formula. For water, we see that for every mole of H2O, we have 2 moles of hydrogen. Setting this up stoichiometrically, we would see that if we have our 0.1665 moles of H2O, and for every mole of water, we actually have 2 moles of hydrogen, well then we're effectively just have to multiply this number by 2. And that gives us 0.3330 moles of hydrogen. And this is our moles of hydrogen. Okay, let's keep these numbers in mind. I'm just going to clear this up to make some room for the next step. But now that we have our moles of carbon and hydrogen, which we derived from the masses of carbon dioxide and water that were given to us in the problem, we can now get our masses of carbon and of hydrogen. So, if you remember, we had 0.1667 moles of carbon, which again, if now we just multiply by the molar mass of carbon given to us in our periodic table, that would give us an answer of 2.002 grams of carbon. Same exact deal with our hydrogen, 0.3330 moles of hydrogen multiplied by the molar mass, the periodic table, cancel out moles, gives us 0.3357 moles of hydrogen. Excuse me, that should be grams of hydrogen. So, what do we do now? Well, going back to the problem, we see that our sample is a 5-gram sample that's composed of carbon, hydrogen, and oxygen. So, if we take that total mass of 5, and from it subtract our mass of carbon and our mass of hydrogen, well, that should just give us our mass of oxygen, right? This 2.662 grams of oxygen, right? Well, actually, no. That is a very common mistake. While it is true that we have a 5-gram sample, which is composed of carbon, hydrogen, and oxygen, it actually is our hydrated sample, right? That means it includes this 5-gram sample. This mass is including that water of hydration. So this 2.662 is not exclusively oxygen. Rather, it is oxygen, but also our water of hydration. So that means that if we wanted to find our mass of oxygen, we would actually have to account for that water of hydration. How do we do that? Well, we take this 2.662 grams and from it subtract the water of hydration. Well, from this 5-gram sample. Where do we get that information? Well, just look right back at our problem. In the problem statement, we see that after heating a separate 5-gram sample of the compound, 0.9 grams of water was lost due to hydration. And that water, due to dehydration, excuse me. And this is our water of hydration. And this is an answer of 1.762 grams. And this is our oxygen. So, now that we have this, we just move about it, or go about it like we did with the other elements. We take this grams, 1.762 grams of oxygen, and convert it into moles. How do we do that? Just divide by our molar mass of oxygen given to us in the periodic table. Canceling out grams of oxygen gives us an answer of 0.1101 moles of oxygen. So, again, let's keep that number in our heads. I will clear this up to make some space for the next step. So, now we have the number of moles for each of the elements that make up this compound. Let's write it out real quick. We have our carbon, of which we have 0.1667 moles. Hydrogen, 0.3330 moles. And our oxygen, which we just found to be 0.1101 moles. So, the next step is just what it would be for any other empirical formula problem, right? We just have to divide by the lowest mole number here to get our mole fraction. And so in this case, that number is clearly 0.101. 0.1101, right? So we would divide each of these numbers by 0.1101, 0.1101, and 0.1101, giving us an approximate value of, or our mole fraction here would be approximately 1.51, 3.03, and well, exactly 1 in this case. And so you may be tempted to just round this 1.51 to 1.5 or to 2 or to even 1, but all of those would be wrong. That is a very common mistake. Again, students are often tempted to just round this number, but we cannot do that. Again, remember, our mole fractions need to be as close to a whole number as possible. So in this case, we would have to multiply by 2 to bring everything to be as close to a whole number. And so doing so gets us to 3.02, 6.06, and well, 2 over here. And this number, or these numbers rather, we are able to round. So this would obviously just become approximately 3. This is approximately 6, and well, this is just, again, 2. And it's these mole fractions that we can then plug in to the general formula. So we see general formula of the compound CaHbOc. just plugging in our mole fractions gives us our empirical formula of C3H6O2. So this right here is the answer to part A, and this is the empirical formula of the anhydrous compound. All right, now that we have this, we can move on to part B, finding the molecular formula of the anhydrous compound. How do we do that? Well, just keep in mind that the molecular formula is really just some multiple of the empirical formula. How do we find exactly what multiple it is? Well, that is why we just first start off by finding the molar mass of the empirical formula. So we already got this answer. I'll just put a check mark there. And now what we would have to do is find the molar mass of our empirical formula. So how we do that, we just do it just like we would with any other compound. We simply, here actually let me write out the empirical formula, C3H6O2. And so now that we have that, we just find the molar mass, again just taking into account the amount of each element in the compound. This gives us an answer of about 74.08 grams per mole. So this number, 74.08, is our molar mass of the empirical formula. And as you can see, this is not the same number as the molar mass that we're given of the actual compound, which means that we would have to, in order to find out exactly what multiple the molecular formula is of the empirical formula, we would just divide these two molar masses. Divide the molar mass that's given of the true compound by that of the empirical formula, which we just calculated. And that gives us an answer of approximately 2. And so what does that mean? It means we would just have to multiply this empirical formula by 2. Right? So, here we go. Let's just clear this up. Simply taking this number, or taking this formula, and multiplying it by 2 gives us C6 instead of C3, H12 instead of H6, and O4 instead of O2. This here is our molecular formula of the anhydrous compound. And now finally we can move on to part C. Let's put a little check mark there. We can move on to part C. What is the value of X in the hydrate form? So what exactly is the hydrate form? Well, again, we can just write a generic formula for this, right? We have the generic formula of the compound CaHbOc, and the hydrated form is XH2O. So how many molecules of water are associated with the compound in the hydrated form? So that value, that X, is what we are trying to find out in part C. How do we do this? Well, the hydrated form, well, that means we're dealing with water, right? So we should look at what parts of the problem are talking about water. Well, here we see that of the 5-gram sample, 0.9 of that is water. 0.9 grams of that is water. So, well, let's just write this out, right? We have a 5-gram sample, and 0.9 grams of that is water. So 4.100 grams of that is the this is the mass of the anhydrous compound. This is the mass of water. So now, just going to moles for each of these, that means that our compound has how many moles of water? Well, we just divide by the molar mass of water, right? We've done that a bunch already. It's pretty straightforward. Cancel out grams. Gives us an answer of 0.04995 moles of H2O. Now, how many moles of the anhydrous compound do we have? Well, that's 4.1. And we have that molar mass of the anhydrous compound given to us in the problem. Cancel out our grams. And that gives us an answer of 0.0277 moles. And so, what are we really trying to find? In that generic formula that we wrote out, that is basically that X is telling us how many water molecules are associated in that with 1 mole of that compound. So what we're really trying to find is the water per mole of compound. Let's just write that out real quick, and it should make sense how we find it if we just write out that statement, actually. We are trying to find the water per mole of compound. So let's just follow this exact formula then, right? We had our moles of water to be 0.04995, and our moles of our compound to be 0.0277, right? And that gives us an answer of about 1.80. So our water per mole of compound is about 1.80, which we can just round to the nearest whole number of 2. So that means, again, we have 2 moles of water per mole of compound, approximately. So going back to our generic form of that equation, XH2O, we can now just plug in all the information we have. We can get our formula of the compound first, right? That should be C6H12O4, and we got that already previously from part B. And now finally this should be 2H2O, right? So this would be our final answer. Well, actually, technically, since we're looking for the value of X, it is this 2 here. That should be the final answer to the problem. And there we go. So, in this rather long and tedious and somewhat complicated empirical formula problem, we were able to find the empirical formula of the anhydrous compound, the molecular formula of the anhydrous compound, and that value of X in the hydrated form. That is the end of the problem, really. So, I hope you guys found this video useful. If you did, please, leave a like, subscribe, leave a comment about, what other problems you may want to see in the future. And I'll see you guys in the next one.